Hello, everyone. We are going to complete Section 3 on Section 10.3 phase transitions by looking at this last learning objective. Describe the processes represented by typical heating and cooling curves and compute heat flows and enthalpy changes accompanying these processes. So we're going to go ahead and look at that. So we'll fast forward through everything we've talked about so far in terms of identifying the three pairs of phase changes, and then we'll talk about heating and cooling curves. As we talk about this, part of this will be review from things that we discussed in Module 5, and then we'll be adding on to this by looking at additional types of ways that we can transfer energy. So you might remember from Chapter 5, the heat equation. So Q, heat, is equal to mass times the specific heat times the temperature change. So that is what happens when heat is causing an object to increase in temperature. It does this thing. We also have heat transfer that causes a phase change. And so we have a different equation for that. And that equation is, I guess we kind of skipped over it. Let's go back up here. So any one of these changes, and this is the first one we looked at, we have these enthalpy of vaporization. So this is energy per amount. These will often be per mole, whereas sometimes your specific heats will be per mass. So just be aware of that. You might have to do some changes when you're doing that particular kind of calculation. This is showing an example of doing that kind of calculation where you're given an amount of the substance. So here it's given as a mass, or I'm sorry, as a volume. It might often be given as a mass. So you do whatever conversions you need to end up with units of energy, so kilojoules here. So you're doing this based off of these values for heats of phase change, so vaporization, or fusion, or sublimation, whichever one you're looking at. So that is the other type of equation. So we have this type of equation, and we have an equation that includes the heat associated with a phase change. So those are essentially, as we talk about heating curves, those are the two possibilities. You can have something that changes the temperature, or you can have something that changes the phase. And a heating curve is making a graph of those changes. So here we're looking at a heating curve. So on this graph, we have the x-axis is the amount of heat added. So that would be probably units of something like kilojoules. On the y-axis, we have temperature. And there are two types of lines you could see on this graph. We have lines that have a slope, and we have lines that are flat. And you'll notice there are different points along this graph where we have either a sloped line or a flat line. So in general, when you have a sloped line, what you are looking at is the energy change because something is changing temperature. And if you look at the graph, that should make sense. So as your amount of heat is going up, your temperature is also going up. They're going up together. So this is when you would use the heat equation. When you have a flat line, you have a phase change. So for the phase change, all of that change occurs at a given temperature, at the temperature of that phase change. So at either the freezing point or the boiling point is where that change will occur. So on a heating curve, you want to be able to recognize where a given type of change is occurring and what type of equation you would use to solve for the energy there. There's a few other details, and I think the best way to describe them is to actually kind of go through this heating curve and talk about what's going on. So it looks like we're starting with ice at -10 degrees Celsius. So as we heat that ice, what's initially going to happen is we're going to heat it from -10 up to 0 degrees. So in this region, we would be using a heat equation where we have the heat capacity is for solid water, so the heat capacity of ice. If you go back to, actually I don't know if we had that table before. Let's see, do we have a, oh actually, yes we did, I'm sorry. If you go back to module 5, there was a table of heat capacities, and if you look on that table, you will see that there is a different heat capacity for ice than for water. So you want to make sure you're getting the right heat capacity if you're doing this equation. For the next chunk of the equation of what's going on, you've gotten the ice warmed up to the freezing point, and then or the melting point, I guess from this direction we would call it the melting point. At the melting point, it no longer increases in temperature. What's going to happen instead is any energy that goes into this ice is going to cause it to melt. Okay, so it starts to melt here, and then it keeps melting as you add heat, and then when you get to this point, it has all melted. In between, along this line, you have a mixture of both solid and liquid. So if you think of, say, any kind of ice water, like if you have a glass of water with ice in it, assuming that you're at equilibrium, all of these would be at 0 degrees. Now, typically what's going to happen there is the ice will melt before it has a chance for everything to reach equilibrium. But that's kind of what's going on here in this example. So once the solid has all melted, then any additional heat that goes into it is going to cause an increase in temperature. So in this region, from 0 degrees Celsius to 100 degrees Celsius, we would use a heat equation based on the heat capacity of liquid water. Okay, so that's what you would use in here. Once you are here, this is the boiling point. Once you have reached the boiling point, you do not increase temperature anymore. Any additional heat that goes in right here is going to cause a change from liquid to gas. So in this region, any heat you add in here is causing that phase change. So it starts to boil, and you have a mix of liquid and gas. And once you've completely evaporated that liquid, at that point the temperature goes up again, and here you would use a heat equation based on the heat capacity of steam. Okay, so that is how you would solve this problem. This problem, if this were a question, say on the homework, you would have 1, 2, 3 heat equations, and then you would have 2 equations based on phase changes, and you would do each of those. You'd have 5 altogether. You'd add all 5 of them together to get the total energy necessary for all of these changes. So what you should be able to do here is either draw or describe a heating curve type of a graph. I would expect for water that that it melts at 0 degrees and boils at 100 degrees. For any other substance, you would have to be provided those temperatures. I would not expect you to know those. But if you were provided with them, could you figure out that information? So you need to be able to either create or describe a heating curve, and then also do those kind of calculations that are based on a heating curve. So there is an example of a calculation here. So this is kind of a classic example similar to what we just discussed. So there will be 5 parts to it, and I will let you see if you can do all 5 of those. So that is a heating curve. That's how we do that. We also talk here about cooling curves. And there's not an example in your text of that, but a cooling curve is simply going in the opposite direction. So if you were to take this and say, okay, we're starting with steam, we're going to cool it down, that would be a cooling curve. So that is it for section 10.3. We're not done talking about phase changes though, because we have more to say about them in section 10.4.